Hey, everybody. Welcome again to another wonderful episode of Howdy Partner here on AWS, Twitch, and LinkedIn. I am your host, James Spencer. You probably know me. I don't know why my camera's fuzzy right now, but that's okay. Joining me today is my co-host, Olabanji. He's stuck in a brick wall for some reason. How you doing, Olabanji?
Great, great. How you doing, James? I didn't know we're streaming on LinkedIn as well. That's great. Good to know.
Yeah, we're trying this out, and hopefully it goes all right. I might have to troubleshoot in a minute, but that's okay. So anyway, Howdy Partner is our weekly show we do here at AWS, and we bring in partners. They come on, they show us what they've built, they show us how they're going to make your life easier, all the cool things they've built on AWS, how they can manage your cloud, anything cool like that. Olabanji, you've been on Howdy Partner before. Do you have any? Did I miss anything?
No, no, but never mind. I'll remind you as if you leave anything behind. I'll remind
Awesome.
you. Yeah.
Okay, cool. And joining us from AWS, semi-regular on the show, especially when it comes to quantum computing partners,
I like
is
that.
Perminder Singh. How you doing, Perminder?
Hi,
Good to have you
hi.
back.
Good to see you both.
Yeah. For people that haven't seen one of your numerous appearances here, you want to introduce yourself, tell us a little bit about what you do?
Sure. I take care of the quantum technology partner at AWS. Have been at AWS for last 4 years now. From last year or so, it just started as out of curiosity. I was attending one of the seminar out in Seattle like 5 years ago, and somebody talked about the quantum. At that time, I was scratching my head. What the heck this is? I'm fast forwarding after 5 years. I'm in mix of it. I mix with a lot of partners who want to build some of the solution around quantum computer, and there are some quantum hardware partner who we have partnered with under Amazon bracket, and one such partner is QuEra. They're out of Boston, Massachusetts. They have rich history associated with Harvard and MIT, and we will learn more as we invite our guest speakers here. We will be joined by Pedro and John from QuEra, and they were founded roughly like 5 years ago. And then they have this computer called as Aquila, which was released last year. And those who are familiar on the quantum side, we call bits as qubits, right? So it's like a 256 qubits machine based on rubidium. And let's hear more from the QuEra folks here. Why don't we invite them?
Yeah, of course. Let's bring them on. For all you viewers in chat, go ahead and get ready with your questions. Make sure you like and follow. And Pedro and John, surprise! How are you doing?
Howdy.
Where are you guys based at today? Are you?
We're in the office. In the office, back in Boston. Just it's down the road.
In Boston, okay.
Yeah, exactly. So, if we've been to Boston, it's down the road from Harvard Business School. So it's in Austin. It used to be kind of a industrial side of the city, and it's been, I don't know, either revitalized or gentrified. Depends on how you how you interpret it.
Awesome. Cool. So yeah, welcome to the show. Good to have you on. QuEra, what do you do? Like, give us a high level. Provide us a brief introduction of what QuEra is and what you guys do.
The briefest introduction is we shoot lasers on that. And by the way, I'm Pedro, and this is John. Just to not cause degeneracy of any kind here. But the briefest introduction is we shoot lasers on atoms, and we make those atoms do calculations using those lasers, right? So it's a pretty cool type of technology that you can take like a gas of rubidium, and you just take this rubidium. So I just saw that there's a question there, and I think it's a timely one. Let's talk about quantum computing in like most basic terms, right? So quantum computing is all about operating systems that are quantum mechanical in nature. Quantum mechanical in nature means that They are very cold and very tiny. And very cold sometimes means that you have to cool down your whole room, your whole laboratory. In our case, we don't. In our case, what we do is we use some laser, and laser is quite an interesting thing, right? It's not like a lightsaber, right? It's not something that is straight. Laser is like it has a little waist, and whenever it has a little waist, it can hold something. It's what we call a tweezer, and every single particle or set of particles that you're holding in place and don't let it move, it's effectively as if you're cooling it down. So that's what we do, right? We hold these atoms, they cool down, and suddenly these quantum properties, they appear, and then what happens is that they start to kind of talk to each other in some abstract way. I don't want to go too deep on that, but the point is that the quantum computing is the process of, like every computing, going from point A to point B, except that instead of regular logic, we use something that we call quantum logic. It's like laws of quantum mechanics that these atoms obey. So that's roughly the idea, right? It's like you want to go from point A to point B, but the road is different. It's not that the car is faster; it's that the road is different.
I think Pedro's given a fantastic explanation of quantum computing in the context of the way our hardware works. I think if I wanted to like sum it up very briefly, there are certain properties inherent to quantum mechanics. I know the term like superposition and entanglement gets thrown around all the time, but the goal of quantum computing is that we're able to use these phenomena to hopefully solve problems in a faster and more efficient manner than our traditional computers can handle.
That's the goal.
That's the goal.
Cool. So with that, I don't know. Perminder, do you have anything to add to that?
I think, it's fair to say, quantum computing is an active area of research. So research being carried out by the enterprise or the research lab out in the world, right? But this is, we are hearing about this term lately, last 2-3 years, right? And then as a community, we started appreciating it more last few years. And why I say that, because 2022, the Nobel Prize for the Physics was awarded in this area, right? But the technology itself is not new. It's 100-year-old technology. What you cannot explain by Newtonian laws of physics, you use that laws at a microscopic level, and you use the quantum mechanics to explain that behavior. So those principles, superposition, entanglement, right? They form the backbone of the quantum computers. So this has been there. There are very important work done by Richard Feynman and then Richard Feynman, and then some of the hyperscaler like right now we are involved in making quantum computer, IBM's D-Wave and all. So this is like a 100-year-old concept. And I think the work which QuEra team is doing is based on something called a neutral atom. I think I would like probably James and Pedro to explain like what is the neutral atom, because there are various modalities. You will hear this term superconducting, you will hear this ion cube, photon-based, but this technology by QuEra is very different from the others.
Yeah, I think we can chat a little bit about that. I think it's an interesting topic. In some way, I see, at least this is my personal view, that neutral atoms it's kind of like a third generation of quantum technologies. There's been other companies or other technologies that have been around for a little while longer. I mean, don't get me wrong. Okay, so the field that we operate in is something called AMO, atomic, molecular, and optical physics. This thing is old. It's old as quantum mechanics. Okay, so this is arguably is what originated quantum mechanics from the beginning, 100 years ago. That's basically the topic. But the type of what I call a second quantum revolution, where we are operating these quantum systems and manipulating them in a controlled way, it's a much more recent thing. And the neutral atom technology is in particular very recent. So I was just telling John, looking at the history of the company, the beginning of the like the technology as it is today, the machines that we have today, was like 2015. It was an empty optical table. I don't know if you ever saw an empty optical table, but I can actually, if you pull the slides, I can show you what an empty optical table looks like.
Yeah, let's pull that up. Which? Oh, this one. Right?
Yeah, there you go. There you
Okay.
go. So you see, it's really like a kind of a metal surface with a bunch of holes where you can kind of screw in mirrors, and you bounce the laser off those mirrors, etc., etc., etc. 2015, it was completely empty, right? And people were architecting something that 2 years later was holding a record number of qubits. 2 more years later was doing operations like a computer. And that's when QuEra kind of spun out of this lab at Harvard. And that's it, right? Like 2 more years, and voila, we have a machine that's a product. This product is this 256 qubit machine that is on AWS bracket, right? It's like, well, it's technically it's here, right? it's like 50 meters from me, but you can access it via AWS bracket service, and it's very distinct for the reasons that we were saying, right? We first of all, we don't have to cool down the environment. We just have to hold these atoms in place. These atoms, they are different from ions. Ions are like you have an atom and then you kind of gotta torture it a little bit, right? You remove some of these electrons, remove some of the charge to charge it. And now these guys, they if you put them close together, they complain because they see each other. The atoms here, they are neutral, so they don't complain. You can pack many of them together, as you're seeing those 256 there, exactly because they are neutral. And it's kind of fun because these guys, they live in kind of an empty space, and like they float in the air being held by this laser. So this means that we can change their position like according to whatever the user wants.
Okay, cool. I love how you're explaining it in a way that like Jasmine said, the ELI5 style. They're not complaining, and you can smash them together a little bit better that way. Excuse me. So you talked a little bit about QuEra and what we do and what quantum computing is. What are we going to show today? Like, I've heard that we're going to talk about Bloqade. I love the Qs and everything, by the way. Aquila and Bloqade.
Right? With a Q and no U, right? As I always tell people.
Yeah. Q, yeah, that never happens. Like, if you ever play Scrabble and you have a Q word without a U, like, that's right. Extra points.
Right. It's a thematic of the quantum computing world. Yeah. Everything has to have some Q in it.
Yeah, right. So I was going to say, from my perspective, like from what I understand, quantum computing is a way, you always think of it discrete, and quantum is more analog. Like, we actually can go in between ones on and off in a way. What is this? I mean, we kind of touched on it a little bit with the atoms, but does it have any relationship to do with the atoms that we're talking about?
Do you want to take this one a little bit?
I don't think I quite understand the question.
Yeah, maybe we can. Yeah,
I'll rephrase it. So, like, analog and digital are sometimes brought up in the context of neutral atoms. What is that all about? I guess I'm trying to say.
All right. So, John.
So I think I can start with the digital component here. I think mainly because there's a lot of pre-existing work in that field. With a lot of the examples that you'll see with quantum computing are usually implied to be digital, where you have like the gate model, if you will. So if you've ever seen those diagrams that almost look like sheet music.
I think I can bring one of those up.
Oh yeah, that'd be okay.
There excellent.
You go. Yeah, okay, awesome. So digital is probably what you've seen or you've probably been exposed to most of the time, with this very like sheet music-like diagram where you have all your qubits in default or initial state on the left, and then we are applying these gates, almost like an analog in normal classical computing would be logic gates. So and or and exclusive or. In the context of quantum computing, we have technically their own 2x2 matrices, if you will. But that's the idea behind digital computing, though, is that you still have you're operating in a regime where you're treating or you're manipulating each of your individual qubits with these quantum gates, if you will. And in the analog mode, Pedro, I think you probably have a nicer explanation.
I can talk about this. Yeah, so it's actually quite interesting the way you put it, because it is really confusing. So most modalities of quantum computing, they talk about this digital mode or gate-based mode. So when we talk about quantum, I think you're right that most we view things discretely, right? And in particular, the bits or qubits, right? The unit of information that you use for operating quantum computers, they are discrete. But what makes digital quantum computing, or what makes gate-based quantum computing digital, is the fact that you see these little boxes, right? I cannot point at the boxes, actually. But you see there's little boxes that say H or RZ or stuff like that, right? So you see that they're individual boxes. These boxes, they represent, as John was mentioning, they are logical operations. They're like, oh, take a 0, turn it into a 1. Or since this thing is quantum, you can turn it into a superposition between 1 and 0 with different probabilities. So I say, oh, it can be 0 with 30% chance and 1 with 70% chance, right? Now, when we talk about analog quantum computing, that's more or less what I'm to depict on the other side here. Right? So here, instead of seeing individual controls and individual logical operations, we have one big logical operation that acts on everybody, right? So all our atoms here, they're gonna see one big logical operation. And instead of saying, oh, do this, now do that, now do the other thing, now do the other thing, you say, start doing this, no, change a little bit, no, come back a little bit. So you can continuously change the instructions. And these instructions, they can be discrete if you want. So a property of our machines is indeed that you can say, oh, give a pulse that hits everybody and send everybody from 0 to 1. But you don't need to do that pulse. You don't need to do a single instruction. You can continuously do different instructions. And this is very important in the quantum computing world, because one thing that is very interesting about these boxes is that when we say logic, right, you expect like, okay, there's an instruction, a set of instructions, a set of rules that cannot be disobeyed. But this is really like a physical apparatus. So it comes with errors, and these operations, these logical operations, they have small errors in the beginning and end of all of them. So whenever you try to control things individually, it's actually quite complicated, because what you may get after you do many instructions, what you may get in the end is not what you were looking for. So controlling things kind of continuously, in some senses, is efficient. It saves a little bit on errors, and that's quite helpful. And also, it allows us to do something that, in some sense, if you want to control each of these qubits individually, I like to draw this picture in which it feels like if you had a high-def TV, right, and a remote control that to change channel, you have one button per pixel.
Oh gosh.
It's not gonna, like, you're not gonna change channels so fast, right? So creating the control lines that allow you to control these guys in tandem in an efficient way, etc., and get the most out of it, is something that is a little tricky if you're just building digital machines. And it's quite cool. So one few other things. So again, the lesson here is that one case is sort of universal. You can do any calculation you want, but it's highly inefficient. While the other case, it's not fully universal, because it's very hard to give any instruction globally to all the qubits like this, but it's quite efficient. You save on errors. And then we can play. So I don't know if you can see well, I guess I know you can see because I'm looking at my friend John's screen here. So this thing that you're seeing, this picture, you actually cannot get it on when using the machine on bracket, but you can get it if you ask us. Holding it hostage. So this picture is actually a picture of a register, a processor. So each little dot is one atom, one rubidium atom that you can see, right? And it's amazing that you can do this with like a microscope and just photography, really. And you can move these guys. So if one day you think that your qubits, for whatever calculation you wanna do, it's nice if they sit in this kind of square lattice pattern. That's fine. But if I don't know, you hit your head, you forgot what you're doing, and tomorrow you want them to sit down in a funky format, shape, right? This thing is called a Kagome lattice, actually. If you've never seen this, it's called a Kagome lattice. You can put them like that. And for something that is maybe a little more visually not impactful, but that you can associate more, you can make the world coast, right? You can position the atoms just like they were in the world coast. If for whatever reason this is an application, this is useful for your application, this is something that we can do and play with like this continuous control over these atoms to do a calculation for you for a problem that maybe benefits from a computer that looks like I don't know, maybe you work in the port industry and yeah,
to do some kind of combinatorial optimization.
Yeah,
where you could conceivably map it onto an arbitrary arrangement of your atoms.
Yeah.
So those arrangements, you're shifting them back and forth. Is that live or is that just switching slides?
Oh no, we're switching slides. We're switching slides. Yeah.
Oh, I was gonna say, I was like, that's pretty impressive to do like just like that, you know.
It is just like that. Okay, you just need to kind of use a little code to choose the geometry, but it's really like positioning in a 2D space. So it's not much more than that.
Okay.
Quite literally.
Yeah.
You give us a list of coordinates, and we can automatically get those atoms in place for you.
Cool. So with that, what kind of real world applications? Like, this is all cool. Don't get me wrong, but like, what can I do with it? Give me some.
No, absolutely.
So if I tack on
one
last point before we move on to the applications here is
sure.
Anyone really curious? There's an interesting parallel as we talk about the difference between analog and digital nodes in quantum computing. It was not long ago, I guess, in the relative history of computers, that in the early days of before quantum, even with classical computing, and there was a period where there's all sorts of different, what I would call experimental computer architectures. This was probably around the time before we even agreed on, a computer should use bytes. There were certainly machines out there with, like 9 bits or 31 or some odd number. But there was a decent period of time where there's interest in analog computers because they were great at solving differential equations better than the computers at the time. And this is, in the realm of classical, pre-quantum and even, pre-modern computing, if you will. Just an interesting historical parallel. And from what I've been told, there may be some revived interest in the classical domain for analog computing in the realm of artificial intelligence and solving.
I think that one there's a great example of what John is talking about. I think that this you're right that it's worth us stopping at this for a moment, because this point lies exactly in the intersection between the previous topic and what James is asking, right? So, like why do this analog computing? And I'm saying that this is efficient but not universal, etc. A great example for this is those Renaissance models for planetary motion, where you had all these, gears and cranks that you put a moon here, and then you start spinning, and then all the other planets, they spin together, and you can see what's the whole motion of this thing. But it's not made from a calculator, right? It's not a calculator. You say, oh, like if I put numbers here, put numbers there, boom, like get to the position of the planet, and now again, and boom, puts the position of the planet again. This would be too slow. So same as analog computing was useful before regular, transistors, digital computing, there is Verdant, a group or some area or collection of researchers and practitioners that believe that the same will apply for quantum computers, that analog machines that can look like a problem and operate like this thing of ports, right? You make the quantum computer look like a problem and then you operate in an analog way. It may be the place where quantum computing is going to be able to get benefit or solve problems first. So I can make a quick stop. Oh, this is a cute animation for. We can come back to it later. But just for the sake of, let's talk soon about how we actually do calculations. I think that it's
right.
we can take a moment to
a nice segue into the earlier question about what problems or things that you can do with the
yeah. But these are the fields or the different topics that we really work on, and it's interesting because if you ask any quantum computing company what they do or what the computers can be used for, it's always the same. Okay, it's always the same. It's machine learning, optimization, and simulation, right? I told you that these machines are not universal, so you cannot solve any problem.
Yeah.
You can certainly solve problems in any area that quantum computers can be useful for, right? So in all areas, although you will not solve any problem. And I don't know. Is this do you want us to get to specifics? Like talk about some specific cases of how we use this, or?
Yeah, I mean, I was thinking Oh no, go ahead.
I can, since I see this machine learning optimization simulation, so I'm actively doing my thesis, a master thesis, and then topic of the thesis is the quantum machine learning, and the what we call on the quantum side is like the quantum SVR, the regression problems which we undertake, and on the classical side there are equivalent regression problems which you can solve for time series forecasting, right? Whether it is the stock, in our case it's the electricity price prediction based on the generation from the fossil, non-fossil fuels, as well as the demand coming from the load on the grid, right? So you use those input parameter and you try to predict the price for the electricity, right? It is a nice problem. This comes under the forecasting time series. There is equivalent way of doing that in quantum side too. I'm getting interesting result. We just took the random forest of the classical, and then we use the gate base, not the neutral atom. But we are getting interesting results. It's almost same. Okay. Now I'm sure we have to defend that topic, defend the thesis. But those are kind of the application. Whether it is a classification, if it's a image classification, the thought. In the mind of researcher is how you take that hardware and apply some of the capability of this quantum processor units to do some of the tasks better, right? Whether it's the image analysis and the classifications. There is a nice little experiment, which some of the notebook which we have on our bracket side, and also in the other hyperscaler, like use the quantum computer to what we call digital digits, which is like 1, 2, 3, 4, like how you do that recognition of those digits better. So there is like a lot of work which still needs to be done. The qubit limit is what preventing us to have full quantum advantage. Right. So what I mean by that is like as the number of the qubits will start increasing, right, from the 256 what we see on QuEra side to 1,000 to 10,000 to 1,000,000, those applications which will provide the true business value because of quantum advantage, that is what we are aiming for, right? And that step is not sequential; it is iterative. Remember, you have a hardware, you have a software. hardware will make us progress from qubit to qubit, right? Like they will increase their count. At the same time, the companies who are focusing on the compiler and they have their, drug formulation, line of business application or some financial calculation, they are interested in knowing about how they have to format their program in the new way, right? So they will start experimenting today. They will also evolve, but at a certain stage in the history, right? And future, we will see that advantage. So all those use cases, what you saw on the screen, what you're seeing on the screen, right? The simulation, it's very hard to simulate the molecules, right? For the drug and the pharma company. So promise or the which quantum computer tell us is like, the discovery of the new materials or the new molecule simulation will be easier. And then as time progress and qubit count increases, we will see the direct impact of this technology in terms of like shortening the life cycle of the drug discovery, right? We would probably have to see the intersection of the quantum with the AI, right? How you can improve machine learning using the AI, quantum in the AI, and a reverse too, like machine learning in the quantum. So all of these are interesting use cases, and some of our partners who come from the software side, right? They actively are using devices from QuEra and other modality to start. They started experimenting it with changing their code base and see like how it evolves. So I think like in past we did some couple of session here and the Howdy partner. One such company was Good Chemistry, right? So they bread and butter is the drug discovery and material, new materials discovery. So the story here is it's like collective effort, right? Collective effort from companies like QuEra to enhance their hardware as time progress from 2023 to 24, 25. And then in parallel, what we have to do from a software side is like start evolving your software to run against those machines. So it's like an iterative approach, small steps, incremental steps. So what we don't want to do is like wait for, a million qubit machine and then, we start changing our software stack or compiler stack, because then it will be too late. If you start early, you're early Sherpa, you discover, you know how you have to reach to the top. That would be the key differentiator between all of the software companies. Sorry, it was like a long answer, but there is a proof out there.
If we can add anything to that, it's just that so more qubits matter, but the quality of them also matters, right? So these objects, they have to, as I said, there's some noise, there's some natural interference that happens from the outside world into these machines, right? It's an experimental apparatus. And it's very sensitive. So getting more qubits, in particular for neutral atoms, it's something that I also like to highlight. Getting more qubits is not a problem. Okay, so we don't have to design, we don't have to make like CAD drawings of what the chips look like and plan for it. No. If you want more atoms, we give you more atoms. You give us more laser, we split more atoms. Okay, and actually, I can even show later a picture of a friend of ours from Chicago, who was he had one of his students create a picture of a field of view of one of like a microscope objective that would pick up 10,000 qubits, just to show that you could fit inside one single like lens, right, or one single neutral atom quantum computer vacuum chamber. You could fit 10,000 of them. Right? So you won't be putting them there because that was not enough laser power, but just to show that all the structure is there. You just get more laser power, you can add more. Adding just more qubits is not enough. Okay, so you need to be able to control them. Your control channels, they have to be kind of efficient. You should not, as I was saying, you should not try to have one little button for every qubit that you want to control, because that's going to be very hard to scale. If you think about your own laptop, you also don't control every single transistor in it at every moment. Okay, so there's such a thing as a bus of information. There's RAM memory, there's processing area. So you have to create a system to control your computer that makes sense at this large scale, and that's what we are trying to build here. Other than that, I am pretty much in agreement with Perminder that there is a very long process that involves hardware development, but also algorithm development. I am not positive if somebody dropped today with 1,000 qubits, perfect qubits, no error, somehow miracle happened, right? Somebody dropped 1,000 here today. It's not obvious that people know already what to do with them.
Okay.
Yeah.
That is true. That is true.
Cool. Yeah, what was I gonna say? I think this is cool. Like, and also like Perminder said, we had another partner that another quantum partner as well that was doing materials and chemistry simulations, and that was a super cool use case to see. You know, in that way, rather than having to actually, you know, physically try and do all these experiments and do these theory, like having that ability to do them through quantum is, you know, way more powerful. Definitely. Sorry. No.
Oh no, sorry, I didn't mean to cut you off or anything.
No, I'm just trying to hand wave, I guess.
No. I mean, it's. I mean, you hit the nail on the head in that. I'm thinking in terms of the historical context. I think one of the earliest proponents for the idea of a quantum computer, Richard Feynman, and you know, his original proposal was like, well, if you had some quantum system that you could finally control and manipulate, you could use it as a test bed, if you will, or platform for quantum simulation, which is pretty advantageous because at the time of Feynman, they already realized there's an issue. If we keep trying to make larger and larger quantum systems to simulate on classical computers, the resource growth, especially in terms of memory, is exponential. It becomes incredibly prohibitive. Even if you throw in some approximations and you try and like make that to make this problem easier, but then that comes with some deleterious side effects, such as your system is no longer accurate to what you're originally simulating. Excuse me. So that was one of the advantages with these quantum computers, especially with our platform as well, is quantum simulation for stuff like condensed matter physics or chemistry. It proves to be a really neat tool in terms of experimenting in that domain.
I would like to highlight that Feynman, however smart he was, or he liked to claim to be, he was still operating 50 years before, before today, 50 years less of information than what we have, right? Yeah. Or 40, let's say. I think that today we learned a lot of how to actually do efficient classical simulations of several quantum systems, but I don't disagree with John that particularly doing dynamics, right? Studying like, what is a quantum system doing as function of time in a 2D system, and you're looking for how these things are behaving. It's like trying to imagine that you have a tree and there's wind passing by, and you want to create a computer image of every single leaf moving on the tree, right? It's very, very difficult. It's very computing intensive, you can imagine, to do that. Now, if any piece of material doesn't have like a million leaves, right? It has 10 to the 23 of those. So it's much, much worse.
Cool. So I don't know if you wanted to dive in and tell everyone. It says, what problems can QuEra's Aquila? Okay. Do we say Aquila or Aquila? How do we say this?
So we have an Italian employee here who once we baptized the machine, he said that the correct name is Aquila. So I say Aquila, and it sounds right to my Portuguese as well. So I feel comfortable with Aquila. So I guess that's it.
Okay, Aquila. So I don't know what is it? I mean, we see it on the screen. What is Aquila?
Right. So Aquila is this machine. Let me if I have a picture of it here. Oh yeah, there we go. Yeah, there we go. Right, so that's what the machine looks like. That's a photograph of the external side of the machine, post photoshopping, right? For but I swear that everything else is real, right? The light inside is for effect. Okay, when you actually are operating the machine, the wavelengths that we use, some of them are in the visible range, but not all of it. It doesn't make such a cool light inside. And the types of problems, again, this machine is available on AWS. So if you even want to set a link to the AWS page of Aquila, you can add it there as well. But different things that have been done with Aquila. Let me stick to that point. So one of them, to Perminder's point of machine learning, one thing that we have been playing a lot with is something called reservoir computing.
Mm-hmm.
So what's reservoir computing? Reservoir computing is a methodology for doing machine learning, where instead of training bazillion degrees of variables like these large language models that's extremely consuming from a computational point of view, right? Like you burn like a lot of GPU power on that and the energy, etc., etc. So what we do is a little different, right? So we take, for example, an image like that horse you're saying. Just for the sake of simplification, we do a little bit of a simplification of key information of that image, but in principle, with enough qubits, you don't need that. You just take the image as it is. And then we say, okay, I have a bunch of atoms. I take lasers on each of those atoms, and each little pixel of that image is going to be a laser that is going to be a little more intense or a little less intense. And now I give it a kick. Woo! The thing starts doing whatever atoms do, right? Like whatever. Like if I were an atom, what would I be doing on a Saturday morning? Like, so they would go for brunch. They would they invite their friends. They would go together. So they do something. So what do we do with that? We look at correlations. We take pictures of those atoms and say, oh, this atom is doing this. Oh, that atom is doing that. These two atoms together, they are doing something else. We make a collection of that information, and then we use this new structure to classify the image. Was that a horse or was that not a horse? Was that what was that? Right? In fact, this method it's quite interesting. We have been able to demonstrate, at least at a simulation of our quantum machine level of our quantum machines, we have been able to demonstrate that we can do multi-class classification. So not only binary. Oh, is it a horse? Is it a camel? Right? But we were able to see like, oh, horse, camel, cat, dog. We are able to demonstrate like 10 classes for this, which, as far as we know, is pretty much a record for quantum machines or quantum algorithms. And experiments on Aquila herself or itself, they are ongoing right now. We are very excited. This is actually, most quantum machine learning methods today are deployed on a laptop. They're not deployed on a quantum machine. And for the first time, we are actually seeing a quantum computer that can learn something. I'm not going to claim that it learns better than like a bazillion of GPUs. I'm saying that this is the beginning of an era where quantum machines can learn, and how better they will perform with respect to GPUs, etc. This is very much kind of, the jury's out there. Okay? But this is something that we started to see already, and one type of application that we are actively working on. And I don't know if John wants to talk a little bit about maximum independent sets.
Yeah, so that's one combinatorial optimization problem. And then just to break it down, combinatorial optimization is just one of those, especially in academia, there's always like a fancy term for things that I think the layperson is already very familiar with in their lives, but need to make it sound a little more official. The idea that you have a problem where the solutions are discrete components, if you will, or even, you could, if I'm playing fast and loose here, you could even think of countable, as in like a lot of puzzle pieces, for example. You have a puzzle and you're trying to put the pieces together. You only have a certain countable number of combinations versus if I gave you a black box with a bunch of knobs on it, well, then you have all these continuous values you have to mess around with.
How many ways can I take my delivery to a given apartment, to given traffic? Right. How many ways? How many routes there are?
My favorite example is something I think a lot of computer science students are familiar with this, but it's if you imagine yourself a courier with a backpack, you have a fixed amount of space in that backpack, and you're tasked with shipping different parcel sizes, if you will. And the problem is, as a courier, you want to maximize the amount of revenue you make per trip. But the problem is your boxes have these different sizes, but it's not always the case that a bigger box means more money for you. You could have a very large box that only ends up being maybe a couple dollars worth of merchandise inside, or you could maybe be shipping somebody's engagement ring, which is a very tiny box that's worth many hundreds or thousands of dollars. So a problem like that is a combinatorial optimization problem. And tying that back to, I think Pedro already mentioned in this slide we have here on the maximum independence set, that is also a particular kind of combinatorial optimization problem that for our hardware platform is we're really amenable to solving that problem. The idea of what the maximum independence set is, in this case, you see those, these very colorful circles, and there are lines between them. So that's our graph, if you will. And the idea behind the MIS is to find the largest number of these circles such that they don't have a neighbor, if you will. Or sorry, I think
an edge between them, right? If they cannot be, there's this little white arrow sticks, right? Two of them that are connected by a stick cannot be read at the same time.
And you're trying to find the largest number of, essentially the largest number of circles you can make red, if you will. And in terms of the real world, what what use does MIS have? You can imagine for cell towers, for example. Like I know these days 5G is popping up everywhere, but in some radio communications context, there's a problem where if you have two towers that are too close together, they end up interfering with each other. But at the same time, your other constraint is you want to maximize the amount of coverage you have while minimizing the interference. So if you can imagine all these vertices are potential vertices or circles are potential locations you could put a cell tower at. And then you can apply or trying to find the MIS of this graph to understand, okay, here's how we can maximize the number of cell towers we have while minimizing the potential conflict, because we don't want two towers to be too close to each other.
Let me see if I have here we go, right? Let's say what I'm in Manhattan. Right. So if anyone in the audience never saw Manhattan, this is Manhattan, right? or at least behind that net is Manhattan, right? That web. And if these are positions where you could place your tower, and the little black edges would be like two towers that would interfere with each other if placed at the same time. It doesn't need to be towers, by the way. This could be what Starbucks in Manhattan.
I was just about to say that one. Yeah.
In Boston, we like Dunkin' Donuts, right? So you don't want to place too many of those close together, because those stores will compete for audience, for customer base, but you don't want to put them too far apart, because then you are not selling as much as you could. And if you never saw Manhattan, you certainly have never seen Manhattan in atoms. And this is what Manhattan looks in atoms, right? So this is exactly what I'm saying, that we can leverage the geometry of your system, right, to place the atoms according to the geometry, and boom, get the best solution for your problem.
Oh, okay. I get it now. Yeah.
You get it?
Yeah.
Yeah.
Because at first, yeah, I was like the first picture. I was like, wait, those all look all too connected and too close. But when you show the last one, that makes sense now. Okay.
Yeah. So one part of them you want to paint in red.
Yeah.
And all of them, because of this process here, that's what I was trying to show, which is, okay, you take your atoms, you trap them with your laser light, right? And now that's an atom. And you can put two of them together. Now, the trick is that you can shine laser, and when you shine laser on these atoms, they puff up, right? They puff up. And if they're too far apart, they can puff up together. But if you put them together, like more close together, that's what I mean, and I try to puff up, the other refuses to puff up. Now you can imagine that an atom that puffed up is a tower that I do want to place, or the one that does not puff up is a tower that I'm like, okay, no, I have to choose one of the two, and that's the one I chose. For two, it's easy, right? It's one or the other. But when you put a bunch of them side by side, that becomes a difficult problem. That can become a difficult problem is the correct, the precise statement.
Just an additional little fun fact there for any physics fans. These Rydberg atoms, like when we mean, like they literally do get bigger in size. And I think the largest Rydberg atom out there is about the width of a human hair. So if you can think of, I mean, we don't do that in our machine, but there experimental an experiment
micrometer size. I don't think that we don't do it in our machine.
Oh, all right.
Okay. So I mean, the typical size of an atom is an angstrom. That's 10 to the minus 10 meters, right? So this is okay. Sorry. I think in meters, right? sorry, not sorry. Right. But when you give energy to these atoms, the electronic cloud, it kind of it can get much larger. So these atoms, they increase 1,000-fold. And you're right, they get micrometer size. Perhaps it's still like maybe 10 times thinner than a human hair, but it's roughly the size.
It's gigantic.
It's gigantic.
It's to the point where if you remember, I think they probably bring this up in maybe like the later stages of high school chemistry, or maybe like even in the beginning of college, and you learn like the traditional atom diagram that you see in popular culture, where you have like your electron is like a tiny sphere orbiting a nucleus with a bigger sphere. These Rydberg atoms can get so big that you can actually see the electron almost orbit with a very classical-like behavior. Whereas we're in the realm of quantum mechanics, you're traditionally taught, oh, there's an electron cloud, in which case you shouldn't think of a periodic orbit, but you should think of some probabilistic spread of where this electron can be.
Which, by the way, is exactly what we see in our machines.
Yes, yes. But I mean for some more cases.
Right.
You can see this classical.
Just quick fact check, right? A typical human hair is 70 microns apart. The 70 microns is the size of our processor. Okay, 70 micrometer by 70 micrometer, 75 technically. The processor that anyone in the audience can access on Bloqade is 75 by 75. So our atoms will be separated by 4 microns ish. So there's a factor of 10 there, but it's 10 times thinner than a human hair. 10 times smaller than a human hair is pretty big for an atom.
I think it might have been a chinchilla. I know that sounds very silly, like the chinchilla, but I remember is because there is someone at AWS. Brad told me about this experiment. I might be getting it mixed up, but there's like it is the width of some hair, and it's probably maybe not a human hair, but one of the animals out there, a chinchilla hair, which I imagine
if it's very fluffy, the fluffier.
But I digress. I just wanted to throw that fun fact out there for any physics fans that are watching right now.
Yeah, no, you're bringing back some of my. I was gonna say, number one, I was like, wait, so you can increase the size of an atom, and then when you mentioned classical orbit, like I instantly thought, I was like, wait a second, if I remember correctly, I always remember thinking of electrons as a cloud, like, so having that and being able to see, a traditional orbit, that's pretty wild. Oh, I had another question. How big is the Aquila machine? Like you showed the picture.
The picture you were seeing? give me in feet, right?
In
So
feet, I
most
don't-
of maybe that's gonna be more friendly for most of the audience. I don't even know if that's more friendly for most of the audience. Maybe a couple meters by a meter.
I mean, I didn't even think of like. I mean, I think it's honorable that you're thinking in terms of numbers. I was just thinking like, oh, if you took like a standard kitchen fridge or something.
Yeah.
Like
Three
taller. Yeah, three. Maybe I got three of them.
as tall as a fridge ish.
Probably a little taller.
A little taller. A fridge and a freezer. And maybe
three of them.
Three fridges wide. So we are kind of in the ENIAC era. For I don't remember the ENIAC, or I have seen pictures of the ENIAC.
A bunch of walls and walls of vacuum tubes.
But here's the catch, right? For 256 qubits, it's 3 fridges. For 1,000 qubits, it's 3 fridges. For 10,000 qubits, it's 3 fridges. This thing is not going to scale in size. Oh, we got a question here, Olabanji?
Yes, I'm looking at all these formulas and I'm thinking in my head, do I need to be I've studied maths major in school or something relative to be able to do this, or it's information is out there for those that wants to study quantum computing? Because to me this is a lot of formula, and this just takes me back to my high school days where I have to memorize this to be able to solve a question and stuff like that.
No, it's not. We can be more heartful about it. It's not just memorize. We gotta celebrate knowledge here. I am a deep lover of this, so I'm not really afraid. But yeah, so there is information out there. In fact, John and I, we have put together a GitHub repo of educational materials. Quite often we hold training sessions as well. And these training sessions, they cover topics that go from the very functionality of Aquila, something that most users don't necessarily need to know, but I think that their experience is enhanced by knowing how the functionality works, all the way to programming it. How do you program it? And at that point, I gotta say that if you have a very computer science background, I guess you have a computer science. So John's background is computer science. My background is physics. I'm a physicist by training. I have to say that without trying to make anyone afraid, you have to program in micrometers and megahertz. That's something that I find it's kind of a cute aspect of programming our machines, that you don't just give instructions. You give instructions with physical units because you are talking directly to a physical system, right? And we appreciate that not everybody might have the background for that. But we have really making it very easy to program with Bloqade, our software, which might be a good segue. And by not only making Bloqade very accessible, but also by creating a curriculum and delivering this curriculum to all audiences. Actually, just last month, we were doing a large training session together with Womanium, this nonprofit organization. Where at the end of the day, we have more than 400 people trained in how to operate our machine. So we are really, really spreading the word, and people are getting into it because it's fun.
You definitely make it sound fun. And I just noticed right now, entanglement through the Rydberg blockade. I just noticed that.
That's where it gets its name.
That's fair, yeah.
I dropped the link to the repo that I just noticed I typed it up a little bit wrong, but the educational repo that they were talking about. I dropped it in the chat, and there's also a scrolling across there on the banner. Just real quick, if you're just tuning in, welcome to Howdy Partner. My name is James Spencer. I'm a Partner Solutions Architect at AWS. Howdy Partners are a show where we bring on all of our AWS partners. They teach us about all the awesome stuff they built. We're talking to Pedro and John from QuEra right now. They're giving us all the information explaining how to use quantum, what it can be used for, and we're going to be diving into their Bloqade solution in just a little bit. I'm going to stop talking because no one wants to hear me talk. I talk too much. So back to Pedro and John. If you wanted to dive into your demo or wherever you're going next.
Poppy56 dropped a question for us, it seems.
Yeah.
Do you want to take a moment to address it?
I feel like you probably have a much to answer.
So the question is, the question is right there for everyone, right? I heard that quantum computers would render security obsolete. Can I crack passwords with this service? So the claim is no and no. I don't think that quantum computers will render security obsolete. So this whole idea comes from probably what is the most famous algorithm for quantum computing. It's called the Shor's factoring algorithm.
Integer poster child for quantum computing.
That's true. So it's a computing process, right? An algorithm that allows you to take a big integer number and tell if that integer is it's a prime or not, and if not, it allows you to figure out what are the factors, right? Prime like 2, 3, 5, 7, and I'll stop there. This process is what lies behind a lot of the RSA or security protocols. Yeah. And Peter Shor, this professor at MIT, he figured out that with quantum logic, as opposed to classical regular logic, you could, in principle, solve this question of factoring this integer exponentially with exponentially less queries, resources.
I think so.
Yeah, I don't know if I want to call them that queries or resources, okay? But absolutely, I don't want to call it faster, okay? Because speed is not just about the logic, how many logical steps. It's also about what's the clock. So there are many factors that go into it. Now, it's true that if something takes exponentially less instructions, most likely, even if your clock of your computer is lower, you will still be exponentially faster. You'll still get to the end much faster than otherwise. But I think that's something that people don't always appreciate is that very likely, at least for early quantum computers, today, we cannot crack passwords yet. When we get to the point of cracking passwords, most likely that's still going to take a few months. So it's not like, you are in a conflict with somebody and that person or group sends an encrypted message saying, I'm going to do something very not nice to somebody tomorrow, right? So I can crack it up and get ready. Look, by the time you are done, tomorrow will be past. Okay, so if it's more like, if 1 year from now I have some crazy idea, then maybe you can crack it in 6 months, and then you can take the other 6 months getting ready for it. So we are way far from that. Way far from that.
Just to piggyback on up here before we get into our demo. There's also a sort of a sprouting domain within like this community of quantum computing. It's post-quantum cryptography.
That's true.
Certainly a domain of interest to find problems or some encryption schemes would prove even to be difficult for quantum computers to tackle. And I think that we've probably heard of some interesting work from the National Institute for Standards and Technology, or NIST, where they usually hold a competition for new cryptographic schemes, if you will. And I think the latest ones have some cool names like Kyber, in like the Kyber crystal. And,
cool.
Yes, lightsabers. So I think even though Pedro does mention certainly these quantum computers getting powerful, but at the same time, I think there's a healthy body of research going on into how can we prepare for these more powerful systems, or the risk of having having quantum computers that could.
Don't want to dismiss it, okay? Don't want to dismiss it. All I'm going to say is that this is not a huge risk so soon, so fast, as I can tell. And out of everything that is good and cool that we can do with the quantum computer, I think that cracking passwords is not my first choice.
It takes a large number of qubits and a large number of really good qubits too. I think we're talking about how it's not just the fact that you have a large number of qubits, but they also have to have a good, very high, I think from a throwdown is like fidelity. So
shall we jump in on how you program this machine? I guess we were moving to that segue, and the transition has been like a very long.
Certainly a good question.
Yeah, absolutely. So let's just jump a little bit. I have plenty of things to say here, but we can.
Gosh.
Yeah, I mean, there's lots of information. Let's talk about Bloqade a little bit. And so we were saying that Rydberg Bloqade is a key aspect of programming our machines, and so much that we made Bloqade the name of our software. Bloqade is both an SDK, meaning it's how you program Aquila, or can be one of the ways that you can program Aquila. Bracket has their own method as well. But Bloqade also works as an efficient emulator to our machine, meaning that if you don't want to run a quantum job right away and pay for it, of course, you can still do the emulation on your own laptop or even on high-performance computing resources, and test your program. Make sure that your program is really doing what you want it to do before you have to commit to run it on the real hardware. How much does it cost? It's actually not so expensive. So for every shot that you want to run, so quantum computing requires you to build statistics. Okay, so you have to do the same calculation several times. So a single shot on AWS costs 1 cent. Okay, and with 100 shots, you can get data for a lot. Like 100 shots with 256 qubits, it's a lot of quantum data.
Also, the like for a collection of shots, right, we consider that under one task, if you will.
Yeah, that costs another 30 cents.
Right,
yeah,
so per task, 30 cents, and then for each shot, if you will, literally, you can interpret it as like a one photo, if you will, of the atom. That's as you said, 1 cent.
Yeah, so if you put $100 on using this, you can get a lot of data out and a lot of and when you think about $100, I know like $100 is not pocket money necessarily, but when you think about operations, right, solutions to problems, like people put much more than that on operating large clusters of GPUs, large clusters. People can put much more than that on EC2 instances for sure.
I know. I put a decent hunk of into those EC2 instances for benchmarking purposes.
Right. And John here is Bloqade's puppies and mummies, right?
I'm one of the developers behind Bloqade. I'm certainly not the original creator, if you will, but one of my jobs is to help develop new features for Bloqade and maintain it, and as part of our mission to make not just a neutral atom quantum computing easier, but quantum computing in general.
Well, what's the name of your position? Maybe you should.
Oh yes, scientific software developer.
So Bloqade is a scientific software, and this means like it's a software for scientific purposes. This is a thing in the quantum field, right? Like it's not just software; it's software for a specific purpose. I mean, there's plenty out there. If you go for Mathematica, MATLAB, and several others that have been around for decades and people know of. Right? And, these are a few features of Bloqade, and maybe do we want to do a quick demo of Bloqade?
Yeah, sure. If you wanted to show the example that you had.
And so I will take a look at that, and we will tell you more about how you can access Bloqade, because you can also access Bloqade on AWS, but we will get there in a moment. So let me share a different screen. Oh, I have to stop and restart.
Yeah, that's fine.
That's okay.
I'll pull it. Yeah, I'll pull you back up.
Yeah. Boom. So this notebook here, you can find it actually on our. I guess everybody can see it. Yeah, you can see it. So this notebook is accessible exactly on that educational repo. So
okay.
everybody can look at it. those educational materials, by the way, anyone can follow them by themselves. Okay, so everything is self-contained. So if you take lesson 1 and go, you can get to lesson 5, to the end of lesson 5. But experience talking to us is always helps a little bit, right? But let me give you a little bit of a feeling of what it looks like to solve this maximum independent set on Bloqade. So the process, I like to say that there's 5 steps to programming our computer. First of them is choose the geometry. The second of them is to choose the time dependence of certain parameters, energetics of our atoms. That choice is the same thing as choosing an algorithm, okay, saying what this thing has to do. After that, you just initialize, compute, and measure. Okay, so initialize, compute, and measure is just technical steps that go into this, but figuring out your program is just the first 2 steps. The first one is, what do you want your processor to look like? Second one is, what's the calculation that you want to do? And here, Bloqade is written in Julia, by the way. So not everybody is familiar with Julia language. You have never heard of it, James?
I was gonna say I've never even heard of Julia.
Oh yeah, Julia is awesome. Okay, Julia is efficient. Julia is fast. Julia is functional. It's not so much as an object-oriented language as much as it's a functional language.
Huh.
You know this more than I do. You can talk more about Julia than I can.
I should functional in terms of not in terms of the, like, I know in computer programming, functional means that people start thinking of
all language function, right?
But Haskell and Lisp. That's not exactly. I mean, certainly. Ironically enough, I mean, other Julia and other languages, even Python, have started to cannibalize some of the features of these functional programming languages. But Julia itself is not like a purely functional programming language. But it's specifically designed, or one of the major appeals of it, it was designed with a lot of scientific applications in mind. In fact, there's a very famous, I think it's like about a paragraph, where the creators behind Julia, they fully admit that they're intentionally greedy with the design. They want the flexibility of Python with the speed of some of the languages like C and C++, with the convenience factor of MATLAB and R, all in one package. So if you're a physicist or someone working in academia, sciences, it's a very appealing language to work with. That's essentially the tongue that Bloqade operates with. But rest assured, if all you've ever used before is Python, you'll find the syntax to be very familiar. It's very, very close.
It's very yeah. We definitely package things in a way that you don't need to be a Julia expert to be able to run it. So let me just go. Is the screen blurry for anyone else? Yeah. So I don't want to just zoom in.
It looks fine to me.
Is this good?
Yeah.
Hopefully this helps.
Fine with me too. So
yeah.
Okay.
It's funny. I googled Julia programming. I googled the good Julia programming language, and like you just said, the first thing that it popped up is Julia better than Python? Is Julia going to replace Python? So
certainly, definitely like a constant debate, if you will, because I know in the scientific computing community, Python certainly has had a very long history with it. But even then, there are.
It's also a compiled language. Julia, it's kind of
Julia does this the only caveat with that compilation, though, is it's like at what I call like the last minute, if you will. So usually, if you write something in Julia, the first time you run it, it's going to be a little slow, but every subsequent run afterwards will be faster, because that first run is what's used for what they call pre-compilation. And then subsequent runs should be significantly faster.
And that's why it's so efficient. Well, that's one of the reasons why it's efficient.
As long as you aren't doing anything funky with the types, like you're really abusing or changing the types on the fly, type stability is a whole is part of.
And let me take a moment to just explore a little bit more why. So Julia is efficient. And quantum computing, quantum computing needs to be efficient. Okay, so quantum computers are not going to be here to substitute a laptop. They are here to solve hard problems that you would not solve otherwise. So if you want to test quantum computers, if you want to emulate them, if you need something that is performant. One of the reasons why we favor Julia. Okay, so performance matters, and Julia has lots of performance, and Bloqade relies on that, and that's one of the things. So
I think before Pedro starts going through the this example here for solving the MIS in Bloqade, we not only want performance in our SDK, we also want to give users the ability to have a lot of flexibility in terms of how they design and express their problems. And with Python, there are a lot of other quantum SDKs that use Python because Python is naturally, it's a very flexible language to work with. But when you really want performance, what ends up happening is you will find packages that do this linking to like some compiled C or C++ backend, which can work, but it's somewhat fragile, if you will, especially if you try and add more and more features. It gets tricky to get Python and this compiled C to play nice. So it's sort of like classically it's called like the two-language problem, which Julia attempts to solve in granting you a similar degree of flexibility as Python while trying to really reap the benefits of a compiled language.
So let's jump off Julia a little bit.
Okay.
No, it's an interesting topic, but I want to make sure we cover Bloqade.
Yeah.
But so, by the way, Bloqade is open source. Okay, so everybody can contribute. We welcome contributions. There are plenty of opportunities for that. But here's what I'm gonna do is to look. I pre-ran this before to make sure that we didn't have this pre-compilation slow down, so it's gonna be very fast.
Rest assured, though, pre-compilation doesn't take
No, it doesn't take that
hours.
Long. Yeah, but here's the thing, right. So we want to generate, as I said, the first step is to generate your register. Generate your processor. Where do you want your atoms to go, right? And here, what you see is that we are using this Bloqade function that's called generate sites, and we are asking for a square lattice that is 4x4. With a little scale parameter here, right? The distance between two atoms of 4.5 micrometers. So that's what I'm saying, right? You're programming micrometers here. Okay, so you have to tell what's the size of this in micrometers to a maximum of 75 micrometers, right? So if you want on Bloqade, actually you can do whatever you want. But if you want this job to go to Aquila later, you need to obey some constraints of the experimental system. And after that, what we are doing is dropping 20% of this just to keep things exciting. Right? So we're dropping 20% of those things. And by the way, this is there's 13 atoms. So this is the size of a lot of quantum mechanics is all about matrices. Okay, so we are going to be operating on matrices that are size 2 to the power 13 on Bloqade, right here live for you. Okay, so 2 to the power 13 is actually quite large. Okay, it's quite large for simulation. There's some technical aspects here to choose this Bloqade radius that I was saying before. Choosing the Bloqade radius means to figure out. I'll get there. I'll get there. I don't want spoiler alert. I don't want spoilers. All right. So, visual aid is to aid, right? I want people looking at me, right? So the point is to choose the Bloqade radius means to choose a characteristic distance below which two atoms cannot puff up at the same time.
Yeah.
Okay. So it means remember that there was those edges. We are choosing what's the size of those edges. That's what we are doing here, right? And we can pick that up in Bloqade if you just ask for plot and then you ask for the Bloqade radius for a given definition of this Bloqade radius size. It will kindly and nicely plot for you already with you're very hands off. Just tell Bloqade, oh, this is the Bloqade radius. You don't have to go around saying, oh, I want 1 from 1 to 2, 1 to 3. Bloqade does everything for you. Okay. So this in particular is something that we call the King's lattice. because it looks like chess. You know, the king can move one step to the sides and one step in the diagonals. That's why we call this. I've seen people call this the Union Jack also, because it looks like the UK flag. It's the type of structure that we're creating here. Then, so that was the first step, right? First step, fix geometry. Second step is to figure out what you want the different parameters of these atoms to do. And for that, we just use a couple other functions. So there looks like a lot of code here, but there's not much really. There's only two lines that matter. This line, omega, and this line delta.
The delta, yeah.
What these things are doing is to create two functions that in this case look like this. I'm gonna reduce the size so that it's easy to see. So these are what some laser pulses are gonna be looking at the atoms. So there will be laser pulses that will be acting on the atoms, and these atoms will feel some energetic influence. And the way that they're gonna feel those energetic influences is exactly like these two functions. One of them on the left, we call omega, is what's making an atom go from skinny to puff to skinny, right? So it's like it's making them jump, increasing size or decreasing size. The other one is kind of a cost function. It's saying, look, if you get puffed up, right, you get bonus points, right? So in the beginning, it's saying, like, look, don't get puffed up. In the it's saying, look, please get puffed up. Everybody, I want you puffed up. As many of you as possible. Except that there's gonna be this cost because the atoms are close together that they're gonna say, we're not gonna all puff up. So I don't know if you get what's going on, right? The one on the left is saying puff, puff, puff. The one on the right is saying, if you're happy. But there is something that is hidden here that is inside of the machine that is saying, like, these are atoms. If they try to puff up together, they don't want to. There's going to be a limitation there. And that's automatic. You don't have to take care of it. You already took care of it when you fix the geometry. Okay? So those are the first two steps. You fix geometry, you fix time dependence algorithm.
Essentially the waveforms, or
yeah,
the lasers you are shooting at these atoms.
Yeah. And then next step, you define this function that we call Rydberg H. This Rydberg H is nothing but the cost function that you have, the actual cost function that you have for your system. So you feed it geometry, and you feed it the time dependence. So if you remember, we were calling omega and delta, those two functions above. And then after that, you initialize the problem. You're initializing the problem. You're saying, okay, from this cost function, I'm extracting the qubits. I'm saying everybody starts skinny. And we are going to do an evolution. So we're going to drive these guys to do something, to do something according to these functions here. And I'm feeding it the cost function. And I'm saying, look, this is going to be a differential equation. That's something that's hidden behind. We're not going to go through all quantum mechanics here today, okay? But at the end of the day, we are solving a differential equation. So this Schrödinger problem is just a choice of a differential equation solver that you can run. And then finally, you emulate the problem. And it's doing a calculation, and in 2 seconds, it did a quantum emulation of our machine in 2 seconds for 13 atoms, 2 to the 13 matrices. And I'm laughing at the comments coming up. And then all of that, beyond that, is just measure, right? So quantum mechanics involves probability. You just ask for, oh, what are the atoms looking like? So this histogram is saying, oh, there's a large chance of having some atom puffed up, another atom puffed up, another at zero, another at zero, etc., etc. This is hard to read. I appreciate that. So you can simply plot what this looks like on the original lattice. And you can see that this already solved the problem, right? This is the highest chance, the highest probability is exactly to paint those 4 atoms in red. And you can see that if you tried to paint this, instead of 5, you wanted to paint 9, that's no good, right? Because 13 is already red.
Right.
Right? But if you wanted to paint 4 instead of 5, or 2 instead of 4 or 5, you could. So the maximum independent set, MIS, is actually degenerate. There are multiple solutions. And that's actually tied to how hard it is to solve the problem. Okay, so the more, the harder, to be honest.
Yeah.
The harder? Yeah, I think that's correct. That's it, right? So now I'm thinking here. Actually, it might be the easier, given a problem instance, right? Given a problem instance, but you can have multiple solutions because this is a quantum system, so it's probabilistic. And I don't want you to get lost, because again, this notebook is self-contained for educational purposes. But I summarized here everything that we did, and actually everything boiled down to just these steps. First one, I don't think it's fair to call on us, right? Like you have to initialize parameters, so you're just initializing them. It's really just this to do a quantum simulation. This is 1, 4, like 5, 6, 7 lines, 7 lines of code. 7 lines of code, you get an emulation done.
I think it's
This is the repo that I have the right banner up for this one, right? This is.
Yeah, this is in that repo.
Yes.
Yeah. So you can actually see some session 4 of that repo.
Right.
Okay.
I think just to make things slightly more formal here, we started off defining our atom geometry, how you want atoms, what the exact laser pulses that you want to shoot at these atoms, if you will, and you create. Pedro put it nicely as a cost function in the context of MIS, but I think for physicists, we generically just call it a Hamiltonian.
I was trying to not drop the H bomb, right? Yes, we call it a Hamiltonian.
That's why it's Rydberg_H for Rydberg Hamiltonian. And then Pedro's right in that we've intentionally tried to make things a whole lot easier here by simplifying the process of taking that Hamiltonian and putting it into the differential equation solver, because that's how we simulate the dynamics over time. My goodness, I mean, if you're really keen on it, you can look at how we get the parameters right for the D solver. It's not the prettiest thing in the world, but we've tried to do as much heavy lifting as possible on the SDK end, just so that enthusiasts and developers don't need to tweak maybe 100 different differential equation solver parameters to get the best balance between performance and accuracy of result.
Good.
Yeah. Do we have any questions on this? I think that this is a good moment for some questions.
I hope we're good on time too. I know we might be.
No, I think we're good.
Very good. So one question, I was still trying to relate what I saw, because MIS, the red dot and the white dot in your slide, right? We can solve, the whole point is like, we have to solve it for, large data set and a lot of matrices to the power 13 and above and all that. But if there is like a toy problem, I think we ourselves can see like what are those maximum independent set based on our analysis, human analysis itself, right? Like, and that's where we say like, oh, this is connected to the edge, but now this is not connected to the edge. That's why it's the maximum independent set for the node, right? The edge and the vertices is the connection between the neighbor edges, right? So what basically we are trying to do here is this puffing up and puffing down the skin, starting with all skinny and all. Are we trying to put that omega and that delta as a cost function to see like what are my combination to place the cell tower or the sort of or solve problems with like a knapsack problem, right? Like I have a fixed size sack and I have to put the stuff like in a box, right, in a container. Is that what we are trying to do here with the physics, like laser and all, puffing up and puffing down?
Yeah. In the end, yes, right? We are just saying, okay, I have atoms, and these atoms, they look like the vertices of a graph. and I can position them according to a graph instance that I care about for specific logical reasons of a given problem. And then you use lasers to excite them and let them interact, and that's it.
I guess I don't know how much of a fan you are of me throwing in some additional physics, but
Always fan. I'm a physicist. Right? How fan are you of me throwing in some figures? Because I'm terrible at it. Right? If you throw in physics, I love it. But
well, the idea that we have, or this general protocol, if you will, where we start by like increasing the so you saw omega, that's our Rabi frequency. So we try and encourage all the atoms to puff up or get to their Rydberg state, if you will. But then we have another hand, if you will, on the detuning. So we start off with a very high penalty, if you will, to initially kind of deter the atoms all at the same time, saying like, don't get excited. And then we slowly or adiabatically, in fancy physics terms, ramp up to this large positive value. It's idea behind this adiabatic sweep. Which comes from another principle, like the adiabatic principle, where if you could have you start with like a known state or a known Hamiltonian or known
solution to an easy problem, and you slowly modify it into a solution of a hard problem.
Right. Yeah. Or you started that solution of the known problem, and then you slowly kind of mold, if you will, or
you modify slowly the cost function into a hard cost function. You go from an easy cost function to a hard cost function, right? And then you get there, and
thank goodness Pedro's here. I'm not the best at explaining.
You're doing very well. You're doing very well. Don't worry about it. And maybe just to answer a couple questions that are popping up. So people are asking for a couple more use cases. As I was mentioning before, we are working on machine learning methods. This similar type of approach of adiabatic preparation of MIS can be used to study phase transitions of systems, phases of matter, magnets. You can use also the dynamics. So far we have talked about changing things slowly, but you can abruptly change these things as well. When you abruptly change a parameter, it's like you give a kick on the system, and now the system is now you messed up, right? It's like if you had a pendulum, right? You can slowly move the pendulum, or you can just flap it, right?
Snap it, yeah.
Right. So and then it will do whatever it wants, right? Particularly if you any of them side by side. So controlling or studying that quantum dynamics is another type of use cases. The packing problem, that's the knapsack problem, they're related, I guess, or the same that John was mentioning. That's not a native problem of our hardware. So the native problem of our hardware is the maximum independent set. But this maximum independent set is NP hard and NP complete, depending on how you ask the question a little bit. So the point is computationally it's a difficult problem, and you can actually use with classical methods on top of the quantum methods, you can approach other combinatorial optimization problems.
You can essentially translate, and we do have research on this. You can translate other combinatorial optimization problems into this MIS problem and have it solved. Although with our current hardware, I think that's
no, it's on the way. It's on the way.
Yes, I mean, it's on the way. There's an additional feature that needs to be there for to perform this mapping, if you will. But it is feasible. It should be feasible.
And tough love from the third year, but okay.
There was one more. I like this one because I had this question too, and he put it into his words. Is the puffing of the atoms, is it central to the functioning, or is it the method?
So it is an interesting question indeed. It's
a very good question. I think.
It's central to the functioning of our quantum computer today. Okay, so in the future, what we're going to be doing is to operate, instead of this skinny and puffed atom for encoding logic, right? You have 0, 1, 0 skinny, 1 is puffed. or the opposite if you prefer. We will be doing 2 skinny states for memory and 1 puffed state for interaction, for making these things talk to each other. So in that case, the puffing of the atoms is still crucial to the functioning of the computer, but it's not going to be crucial for the encoding of the information. I guess it's also crucial, but in a different way.
So yeah, I didn't mean to cut you off.
No.
Just to piggyback, to add a little extra detail here. Those 2 the skinny states, if you will, or I guess the fancy term is like hyperfine. Hyperfine states is certainly one approach. So basically, you have a pair of energy levels to encode the information, and then we'll use that Rydberg state or the puffing up to get our qubits to interact with each other. So we'll have, you'll have a place to store your data, and then when you want to perform an operation, you have like a 2-qubit logic gate, if you will. Then we'll take advantage of that Rydberg state.
Right. I think that with the advanced time, it would be great if we could just mention a few more things about Bloqade that are probably relevant for the AWS audience. Thing number 1 is that I guess we mentioned not long ago, but for those that arrived later, Bloqade is on the Amazon Marketplace.
The AMI. It's as an Amazon machine image or an AMI.
Yes, exactly. So you can run Bloqade on your own laptop, for sure. But if by any chance you want to, use clusters like the AWS clusters, for example, you don't need to start everything and install Bloqade on your machine. You can just go to the marketplace, you click a button, you choose your EC2 instance, voila, Bloqade is there for you. And there are a few good reasons to do that beyond not keep your laptop hostage while you're running a simulation, right? One of them is, of course, increased compute power, right? More memory and more processing power, so that you can simulate larger systems. So Bloqade today on your laptop, it's going to be hard to go more than 16, 17 atoms. But if you have like maybe 64, 128 RAM memory, maybe you can get to 20 atoms. But
gigabytes, 64 to 100
gigabytes of RAM. Yes.
If we could pull it off in megabytes, oh man, I'd be
That'd be great.
Oh, thank you, thank you. That was a slip. But of course, you can access this kind of resources on EC2, for example. More than that, Bloqade also has a lot of high performance functionality that you can talk about more, John.
Yes. I think before we...
I think we will not have time to... Let's just cover it.
Before I do get into those high performance features, I saw a little bit of confusion around the hyperfine states and the Rydberg states. And so the goal of when we're dealing with hyperfine, and hyperfine you can literally think of as like there are 2 energy levels in your atom that are very close together, is that when we're in that hyperfine state, we're not really... The goal is not to puff up or change the size of the atom anymore. When you're dealing with hyperfine states, store or preserve your quantum information for as long as possible and be robust to certain forms of noise. But when we do puff up that atom is when we want to have, say, 2 qubits interact with each other. So we take advantage of that Rydberg blockade. In fact, there's such thing as a Levine-Pickler gate, or you might see described as an LP gate. That's where we the atoms to puff up, and then to get them to interact, so we can actually have these control gates. So I think in the digital quantum computing realm, you have controlled NOT gates, controlled rotations. That's where we would move out of that hyperfine state.
But to stick to Bloqade.
Yes, sorry. So I saw the confusion in chat, and I'm like, well, let me.
It's okay. There plenty of opportunities for us to talk about these details, but I really think that it's important for the audience to like, this is a product, it's there for you. You can send jobs from Bloqade to Aquila. You can use Bloqade with multi-threading, so you can parallelize operations.
Oh yes. You also have in terms of the multi-threading, that's to save you time on processor power. But we also mentioned, memory is certainly a bottleneck here, where every time you add an extra qubit, it's exponential growth in terms of memory. But one of the tricks we have up our sleeve, and that Bloqade provides, is this subspace approximation, where we, it is admittedly a little bit of cheating, if you will, where we look at your initial atom configuration and you provide us with the Bloqade radius. And if we know that in advance, it's possible to realize through doing like some classical MIS calculation, if you will, that there are certain quantum states that you will not reach, or are exceedingly improbable in terms of reaching, because of this blockading phenomenon.
Product-wise, you can do multi-threading, you can do GPU support,
Right.
you can make your simulations go faster,
right? Or you can cut down on memory too. That's the whole point.
You can cut down on memory.
Subspace approximation.
So there are plenty of things that you can do with it. As far as I can tell, Bloqade is I don't want to say free on the marketplace. It's free from our side. It's an open project. It's an open source software. So you will pay for it whatever you use of EC2 instance. Nothing else, no more. And then the price depends really on the resources that you are picking up, right, and that you're interested in using. But plenty of features: GPU, multi-threading. More memory is always useful. There are plenty of reasons for which you probably want to use this on EC2, and we are also making it easy for you.
Nice. So
Awesome.
any other, Pedro, like any other upcoming event you want to invite the audience, or very focused thing, like what we call it at AWS, call to action,
Yeah.
where developers and researcher can actually go start experimenting with, and then they can contact you guys or even us on the Bracket side, on AWS side. Anything you want to share?
So I think Pedro already hit the nail on the head. Considering the open source nature of Bloqade, on our GitHub repository, there's certainly issues there that we certainly welcome others if they have if they're inclined to tackle. I mean, if there are any like new features you want to propose, or even if you want to go ahead and take a stab at it yourself, by all means, you're certainly encouraged to make a pull request. And Bloqade does have plenty of documentation as well, and we have our educational resources. Pedro, do you have anything you want to add on?
No, I think that's it. I'll stick to that.
Awesome. Well, thank you so much, guys. I dropped a whole bunch of links, especially if you want to check it out, the AWS Marketplace. I don't know why I didn't think of that earlier. That's totally on me. Marketplace is one of the best and easiest ways to get not just QuEra, but like all the AWS solutions out there from our partners. It's just a one-click button, basically, and to get started. Awesome. Thank you so much, Pedro and John, Perminder, Olabanji. This was wonderful. Please check out QuEra and Bloqade. Tune in next week for our next Howdy partner, and we have Pyramid Analytics coming on to join us and do some analysis, as the name implies. And if you can, please take 30 seconds. I've dropped it a dozen times in the chat. I'll do it one more time. Please fill out our survey. Let us know what you liked. It's super, super, super fast. It's like 3, boxes with stars. I'll drop it one more time. And I think that about wraps it up. Please connect with John and Pedro and QuEra on LinkedIn. I'll drop that one more time as well. There we go. They'd love to hear from you. And if you're much smarter than me, go ahead and contribute and do a pull request in Bloqade.
Yeah.
We have like 30 seconds. Anything else? Anyone have any fun plans for the weekend coming up? Nothing? TikTok famous?
Probably a few. But just wanted to thank for the invitation. It's always a pleasure to talk about quantum computing. There's just so much to talk about, from product perspective to concept perspective to where we are and where we are going, and why you should be working with us. So I just thank you, everybody for for staying up with us, and thank you guys for the opportunity to speak. And
awesome.
Look forward to talking more and see you again.
Yeah, absolutely. been
Great.
fantastic, and thank you so much.
Yeah, thank you. All right, everyone. We'll see you later. Have a good day.
Thank you, Pedro John. Thank you, James Olabanji. See you.